Okay, picture this. Imagine a world where your data absolutely has to be acted on instantly. A world where waiting for some nightly batch job to process today's events means you've already lost the window of opportunity, or missed a fraudster, or just showed a user totally stale information. How exactly do modern systems handle this relentless, never-ending flow of information without just buckling under the pressure? Welcome to this explainer on Chapter 12 of Martin Kleppman and Chris Riccomini's Designing Data-Intensive Applications. Today, we're going to follow a single piece of data on its high-speed journey through a modern architecture, zeroing in on the fascinating and sometimes tricky world of stream processing. Here's what we are covering today. We'll start with transmitting streams, then uniting databases and streams. After that, we'll hit processing streams, the complexities of time, advanced stream joins, and we'll wrap it all up with fault tolerance. All right, Section 1, transmitting real-time event streams. Let's get right into how our event actually gets moving in a streaming architecture. So the real game changer here is the contrast between traditional transient messaging systems and modern log-based brokers. Traditional AMQP or JMS brokers are basically like a post office. They route the messages, hand them to consumers, and once they're acknowledged, poof, the message is deleted. It's totally transient. But log-based brokers act like an append-only file on a disk. They durably record the sequence of events, which means multiple consumers can read that exact same history independently without actually destroying the data. The mechanics of this are pretty brilliant. Producers are just appending events right to the end of a log partition, while consumers independently read those messages sequentially. And the consumers use an offset, you can think of it like a bookmark, to track their progress. If a consumer crashes, no big deal, it just restarts and picks up right from its last offset. It's this incredibly robust way to decouple the producers making the data from the consumers analyzing it. Plus, it even lets us rewind and replay historical events if we ever need to. Moving on to Section 2, uniting databases and streams. Traditionally, we've treated databases and streams as two completely separate universes. But what if every single write to a database is actually just an event that we can capture and stream? That brings us to Change Data Capture, or CDC. Instead of keeping database replication logs hidden away as some internal implementation detail, CDC pulls that out into the light. It turns literally every database insert, update, or delete into a real-time event stream that any downstream system can instantly consume. Conceptually, the source database acts as the ultimate truth here. As it captures updates, say setting a value from X to A and then X to B, that entire log of immutable state changes streams out in real time to update derived data systems. So if you need a super fast search index or a data warehouse, you aren't burdening your primary database with massive complex queries. You just let those secondary systems consume the CDC stream and update themselves. If you're mathematically inclined, you'll probably love this analogy from the authors. Think of your application state, the current snapshot of your data, as the integral of an event stream over time. Conversely, a change stream is what you get when you differentiate that state by time. By keeping a durable log of those immutable events, you can always perfectly reproduce the current, mutable state of your application. And that right there is the core principle behind event sourcing. Section 3. Processing and analyzing streams. Okay, so our event is transmitting, it's stored, now we have to actually do something with it. We typically use stream processing for three major things. First, complex event processing, or CEP, where we're hunting for specific patterns, like spotting a credit card fraud sequence as it happens. Second is stream analytics. This is less about finding specific patterns and more about windowed aggregations, like calculating a live average of website traffic. And third, maintaining materialized views. Using techniques like incremental view maintenance, we can continuously update our database caches and views in real time as the stream flows, completely skipping those heavy traditional batch queries. Section 4. The complexities of streaming time. Now, this is where our event's journey gets genuinely weird, because in streaming, time is completely relative. Think about the Star Wars movies for a second. Episode 4 came out in 1977, but Episode 1 didn't drop until 1999. The order you process or watch them in the real world, the release date, doesn't actually match the chronological narrative of the events themselves. Will stream processing algorithms have to be specifically written to handle these exact same discontinuities between when something actually happened and when our system finally sees it?
It really boils down to processing time versus event time. Relying on processing time, which is just the clock on your server, is super easy, but it totally breaks down during network delays or system restarts. Event time, on the other hand, which uses the timestamp on the actual payload, is highly accurate. But it forces us to deal with straggler events. Say a user's mobile app goes offline and uploads its events 3 days later. Your system needs to know exactly how to adjust its historical aggregations to account for that late arriving data.
If you rely entirely on processing time, you're going to create fake data spikes. Let's say a stream processor goes down and events just pile up. When it finally restarts, it processes that massive backlog all at once. Suddenly, it looks like user activity just skyrocketed, even if the actual request rate by event time was perfectly steady. Confusing those two concepts literally leads to bad data and a lot of false alarms. To correctly aggregate data over event time, stream processors use 4 distinct types of time windows. Tumbling windows chunk time into fixed, non-overlapping blocks, like every minute, exactly on the minute. Hopping windows are fixed, but they overlap, so maybe a 5-minute window that advances every 1 minute. Sliding windows smooth things out by looking at events within a strict time distance from one another. And finally, session windows don't even have a fixed duration. They just group events together based on bursts of user activity until the user eventually goes idle. Section 5. Executing advanced stream joins. Let's look at how we combine streams, because an event on its own is rarely enough. We generally separate streaming joins into 3 distinct buckets. A stream join matches 2 recent events together, like a user searching for a URL and then clicking a result 30 seconds later. A stream table join, which is often called enrichment, happens when an activity event arrives and the processor queries a local copy of a database to attach a user profile to it. And finally, a table join merges 2 changelogs, keeping a complex materialized view, like a dynamic social media timeline, constantly updated as new posts and new followers arrive.
Section 6. Ensuring streaming fault tolerance. Ultimately, our event absolutely has to survive system crashes and network partitions. In batch processing, if a job fails, you just run it again. But because streams are infinite, they never stop, so we can't just wait for a job to finish. We need a very specific guarantee known as exactly once semantics. Now, technically, a system might retry processing an event behind the scenes if something fails, but effectively, the final output to the user or the downstream database looks as though the event was processed exactly 1 time. This is absolutely crucial to ensure we don't accidentally double charge a customer's credit card just because the server happened to reboot.
How do stream processors actually achieve this? Usually through one of 2 methods. Frameworks like Spark Streaming use microbatching. They treat the continuous stream as a sequence of tiny 1-second batches that can be retried individually. Other systems, like Apache Flink, use checkpointing. They periodically place a barrier into the message stream itself to generate a rolling, durable snapshot of the system state. If a crash occurs, they just roll the whole thing back to the last checkpoint. But here's the catch. Internal exactly once guarantees don't magically protect your external systems. To protect an external database from getting duplicate outputs if a stream processor restarts, we have to design our operations to be idempotent. That means the operation has the exact same effect whether it's run once or 100 times. By passing along extra metadata like a consumer offset or a unique transaction ID, the external database can recognize duplicates and safely discard them without compounding any errors. So after journeying through transmitting logs, handling the strange relativity of event time, joining complex data streams, and ensuring idempotent fault tolerance, ask yourself, are your systems truly thinking in streams? Are you fully embracing immutable events and real-time state derivation? Or are you just running really fast batch jobs? Understanding these core concepts is absolutely the key to building the resilient, real-time data architectures of tomorrow. Thanks so much for diving into this explainer with me, and keep questioning how your data flows.